Z distribution for that result. It'd be actually the height of the normal 0, 1 random variable. That's my maximum value.
So that was taking the maximum likelihood over the restricted parameter space?
Yes. Yes, it's the maximum likelihood over the 3 parameter spaces, okay?
Where do the weights come in? Where does the 0.95 and the 0.02?
That comes in through Bayes' factor because you get the likelihood ratios and you multiply them by the odds that I've set up there with the 0.95s and the 0.25s, and then I get out the posteriors. It's a very simple calculation. So there's the Bayes factor, which says, quote, without any priors on it, we're 3.35 more likely to be in this region. But if you don't put priors on it, you don't get any probability based. That's what Fisher was saying, okay? Well, you're 0.3 over here and you're 0.2 over here because you're further away from the result. The result is on that left side, on that beneficial side. Well, you can transform, all right, you can transform that into posteriors. And so you flip these to posteriors. Remember what the priors were. We just went through them. So now, this went from 0.25 to 0.085, okay? It was a small sample size in an okay result, so it pushed it a little bit along, all right? That went from 0.95 down, and it's way away from this one, all right? And so it went from 0.25 to 0.005, okay? And so that's what we're talking about there. I guess I should use my pointer. I spent all that time doing that. All right, so here is a summary of where we are. We start off with these. All right, and now we update them to 0.85, 0.005, and 0.91. Isn't that easy? Working with an investigator, don't have to do p-values. You say, here's where we are. I mean, you've got to go through the negotiation on where you start, but all the rest of it is data-driven. So these are posteriors, all right? And now what we have is a little picture. Remember the March of Science diagram, all right, after the Feynman quote? And so we're going from 0.25 to 0.85. Before trial 1 to after trial 1, that's all data generated, okay? And so science marches forward. And so we got our little guy, and he marches forward. Oh, come on. Isn't that cute? Yeah, question?
You call these posteriors, but are they really posteriors? They're really not Bayes calculations.
They're not the same kind of Bayes.
I would not call them posteriors.
Maybe I should think about that.
You know, profile likelihoods adjusted for...
I think you know more about traditional Bayes than I do, and that's one of my weaknesses, yeah.
Well, actually, Richard Royal is one of my colleagues.
Oh, okay.
I thought he did a really good job on the likelihood principle.
Yeah, he did.
Yeah.
He did a great principle, but he stopped short of putting priors on those regions, so he doesn't go to probability based.
Exactly.
Yeah.
Can you go back one slide
Mm-hmm.
to your little march?
Yeah.
Okay, so if you're talking to the investigator,
Yep.
or Dr. Chance is talking to the investigator, what is your interpretation now for that 0.085? How are you interpreting what that 0.085 means?
I'm 8.5% sure that BIOS 266 is superior, but only 8.5%. Okay? So what would you do? What would you do if you were here? You'd run a second trial, right? He gets some money. He says, hey, we got some pretty good results on the first one. He gets some money. He goes back to Jamcatnia. All right? That's where he does this study. That's Jamcatnia. My daughter's names are Jamie and Katie. All right? Goes back to Jamcatnia. He's got a big trial here. He's got 300 kids in a group. All right? He gets the following results. He's got 12.5% difference between the two groups. It's a big trial, so he's got a nice, significant p-value there. He's got a 35 point, almost 36 Bayes factor using this method. He's now pumped that 0.85. It's now up to 0.77 as a posterior. All right? And so we update those as follows, and we're pretty happy. Not happy enough maybe for the FDA. We'd be in a tough, would you approve this drug with these kind of things? But let's say not. And so what we do is we run a third trial. We go back to Jamcatnia for a third rainy season, run it again, all right?
Are those numbers for combining both trials together?
Yep.
Okay.
Yep. You begin with the 0.85 and you're updating it. Yeah, you begin, because now you're just like in traditional Bayes. Your posterior from your first is now your prior for your second.
But there are two calculations you could possibly do. I don't know if those are identical. One of them being that you could collapse the data together into one table.
Yeah, no, they're different.
Yes.
They would be different.
And that's the point about the Bayesian, is
Yeah.
that it's always coherent. And your calculations are not coherent.
No, they wouldn't. No. It doesn't matter which order I put the studies in.
Right.
Yeah, but you also have to remember that the trials are never going to be exactly the same as each other anyway. And I think that data pooling, I think it really hardly ever is able to be done. All right? But you could say, well, at least I'm at this prior. Yeah, not as simply as that. Yeah, this is a pretty contrived example where we're going back to the same place and running the same drug and whatever. No, you're right. So what do we got? We got our guy marching forward. He's now 3/4 of the way down the entire march. So he goes to trial number 3. Trial number 3 was supposed to be 300 cases in a group, but there was a drought in Africa. And I actually worked on a study when I was at the University of Florida. We were doing a clinical trial on malaria in Africa. They went over there and there was a drought. All right? And all that money really went down the toilet. Okay? So what we got here is, all right, we got about 120 odd observations in a group. We get the following results, sort of the same thing we looked in before. We got another non-significant p-value. All right? We got a superior Bayes factor. But look at what happens. Even with this aborted clinical trial with a non-significant z statistic on comparing the two proportions, we've now got a posterior probability up in the 91.5%. All right? And so now we're updating. We're going from 0.77 all the way up to 91, 0.85, and we're really down to nothing over here. All right? And so now we got our guy marching forward to 0.91. And now, and I asked my best friend today, who's professor of religion at University of Miami, Steve Sapp, I said, would you, and his area is also health, I said, would you approve this? And he says, absolutely, because he looked at the 0.91, he looked at the 0.09 under the null, but he saw that the null was all the way over on the efficacy side or whatever, and he saw the less than 0.001 on the harm side, and he said he would approve that. So if Steve will approve it, I'll approve it. All right? So here's some remarks. The two sides of the hypothesis are kept separate. Two sides of the hypothesis, none of this two-tailed test business, okay? There's no point null, no p-values to interpret. Only one of the 3 trials yields a 0.05 or less, all right? But each move the march forward. That's important because if you know what the FDA requires, they require two well-done trials with p-value less than 0.05 to approve, okay? Although trial number 1 was a preliminary study, its results were fully incorporated into all subsequent analyses. The remarks. Trial number 3 was weakened by low recruitment, but still proved very, very valuable. No need to alpha spending here. We're testing one hypothesis. We're just moving along. We don't have 0.05 that we have to divide up along all these interim analyses and all that kind of stuff because we're not playing the p-value game. We're just assessing the same hypothesis over trial time. The ordering of the study makes no difference. So the studies are exchangeable, like I said, and it has to be that way. It wouldn't make any sense any other way. All right. So what if trial number 2 would yield the opposite results? If we just flip those, what do you think would happen? Well, those are the opposite results. Remember that was minus 125 before. All right. P-value is going to be the same, obviously. I've just flipped the 2 groups. Now what you get is you get a Bayes factor of 0 on that side. And now that posterior went from 0.85 down to 0. And so what you have here is obvious, okay? And now what you have is this guy marching backwards. And that's what you would expect to happen. The method works, and it works with common sense, all right? Here's another a priori setup. So suppose you didn't like that setup. Let's do this one very quickly. So here's a range where we're not good enough or essentially null, okay? And we're going to make that the minus 4%. So now we're going to say this isn't marketable unless I can get it down to minus 4% or less, all right? And so we set up, this is now a tougher criterion. It's going to lead to lower posterior probabilities because the criterion is tougher to get to rule into clearly superior. We're going to also change the probabilities. I have complete flexibility here. I'm going to put 0.80 over here, all right? I'm going to put 0.05 over there. I can do anything I want. And I'm going to put 1.5 over there. And I'm going to argue this